Welcome back class. As we studied about the parallel plate capacitor, and today's topic is series combination of the parallel plate capacitor. So let us see the circuit arrangement. So here three capacitors having the capacity C1, C2 and C3 is connected such that they are the tail of the first capacitor is connected with the head of the second one, and the tail of the second one is connected with the head of the third one. And the first head of the first capacitor is connected with the charge source, and the last end of the capacitor of third capacitor is connected at the ground or the zero potential. And the potential difference across the ends of this arrangement is V. That means the total voltage applied across the this setup is V here. And if you connect the voltmeter across the capacitor C1, the reading is V1, and across the C2 is V2, and across the C3 is V3. And because of this potential difference, the charge present on the first capacitor is plus Q, and if it is plus Q, then because of the induction, the second plate of the first capacitor have the minus Q. Similarly, this will get the plus Q and the minus Q, the plus Q and the minus Q. So the charges present on the each capacitor is same. You can see here this plus Q, this is the minus Q, because these two plates is directly connected. That is why the inductive effect is same. So if it is plus Q, then automatically that will be minus Q. And if the electrons are moving this end to this end, the same amount of the positive charge present on the second plate, first plate of the second capacitor, that become plus Q. So plus Q, minus Q, plus Q, minus Q, like this one. So in series combination, we can see that the charge present on the capacitor is same. So few students have some doubts, sir, if the charges present on the capacitor is same, so why the potential is different, right now? So you can see here the formula. You know that this V is equal to Q by C, or Q is equal to C. So V is equal to Q by C. So the potential not only depend upon the charge, also the capacity of the capacitor. So here the capacities are different. Here the C1, this one is the C2, and this one is the C3. So because the capacity is different, that is why the potential across each capacitor is different. So potential is different here. Clear? So in series combination, you know that the potential is divided because the total potential is equal to the potential drop across each circuit element. That means the V is equal to V1 plus V2 plus V3. And how this result is done? Because it is simple law of conservation of energy. Whatever the energy supplied by the cell, the total energy is utilized by the each circuit element. Right now, so it's basically the law of conservation of energy. So V is equal to V1 plus V2 plus V3. And what is the V1? V1 is the potential across the first capacitor C1. So you can write the V1 is equal to, we have the formula V is equal to Q by C. So here the charge is Q and the capacity is C1. So you will write the V1 is equal to is Q upon C1. So Q upon C1. Similarly, for the C2 you can write V2 is equal to Q upon C2, because charge is still, you can see here the charge is same, plus similarly for the C3, Q upon C3, it is your V3. You see here Q is common in the numerator, just take the common. V is equal to Q common in the bracket 1 upon C1 plus 1 upon C2 plus 1 upon C3. Right? Just divide this Q. I am writing this one 1 upon Q by V. Right? Equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. And what is Q by V? From this formula you can see that Q by V is basically the C. Here you can write Q by V is equals to C. Q by V is C. And what is the Q? Q is the total charge supplied by the cell. And what is the V? It is the total voltage or the applied voltage. So here you are getting the Q by V is equal to C, means total charge upon total voltage equals to the total capacitance of the cell. Total capacitance. So in place of Q by V, I can write the total capacitance. So you will write 1 upon C net is equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So this is the formula for the C net for the net capacitance for the series combination. So what is the physical significance of this statement? If you use 3 capacitors of capacity C1, C2, C3, that will draw the same amount of the charge from the same supply if you connect the C net. That means if you connect the C net, that means the one capacitor of this rating, that will also drain the same amount of the charge from the same supply. Right now? So that means whether you use 3 or in place of 3 you can use only one capacitor of the C net. So that C net also will draw the same amount of the charge from the same supply. So this is the concept of the C net. So in series combination, you see the formula 1 upon C net is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Don't be confused. In the series combination of the resistance, you have the formula R net is equal to R1 plus R2 plus R3. Right now, but here in the series combination of the capacitor, you are getting the formula similar to the parallel combination. In their parallel combination, you are getting the 1 upon R net is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. But here in the capacitor, the series combination, you are getting the 1 upon C net is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So this is your series combination. In series combination, all the charges are getting the same amount of the charge, but because of the different capacity, the potential across each capacitor is different. So this is your series combination of the capacitor. Let us discuss the parallel combination of the capacitor. So in the parallel combinations, just see the setup. In the parallel combination, 3 capacitors C1, C2 and C3 is connected such that the head of all the 3 capacitors is connected at one point and tail of all 3 capacitors is connected at the one point. And the supply or the potential difference across the ends of these two, this setup is V volt right now. So because of this potential difference, the charge will start to flow from this point, and see, because the 3 branches are there, so this charge Q will be divided into 3 arms, because here 3 wires are there, so 3 arms are there. That is why this total charge which is supplied by the source is divided into 3 arms. So according to their capacity, the charges will distribute right now. So here I am assuming on C1 the charge is Q1, on C2 the charge is Q2, and on C3 the charge is Q3 right now. And in parallel combination, you know that the potential across all the capacitor is same, because all the head of the capacitor is at one potential and tail is one potential. So if you connect the voltmeter here, you are getting the same reading across each capacitor right now. So in the parallel combination, the potential is constant. So if you apply the law of conservation of charges here, you will get total charge Q is equal to Q1 plus Q2 plus Q3. This is simple, your law of conservation of charge right now. And you can write Q is equal to, what is Q1? We have the formula Q is equal to CV, the basic definition of the capacitance. C is equal to Q by V or Q is equal to CV. So here you can write the charge present on the first capacitor Q1 is equal to how much? The capacity, which is C1, and the potential across this capacitor, which is what? V, because in the parallel combination the potential is same. So in place of Q1 you can write C1 into V. Clear? For the Q2, that means the charge present on the second capacitor, again it is from the same formula, Q is equal to CV, the capacitor C2 and the potential across the second capacitor. Again it is parallel combination, so the potential will be same. So C2 into V. Similarly for the Q3, it is C3 into V. Clear? Now the V term is common in the bracket C1 plus C2 plus C3. Clear? Now put the value here. You will write Q by V is equals to C1 plus C2 plus C3. Now Q by V. From this formula you can write Q by V is equal to C. So here Q is what? Here is Q is the total charge supplied by the power source. So Q is the total charge. and V is what? The total supply. So again you will get the total capacitance of the circuit, total capacitance. So in place of the total charge upon total voltage, you are writing the total capacitance or the net capacitance. C net is equal to C1 plus C2 plus C3. So in the parallel combination, you are getting the net resistance is equals to C1 plus C2 plus C3. Again, the physical significance is same. In place of these three capacitors, you can use only one capacitor of rating C net. That will draw the same amount of the charge from the supply. That will draw the same amount of the charge from the supply, the same supply. Either use these three or you use only one capacitor. Both the cases you will get the same amount of the charge from this supply. Right? So this is your parallel combination. So here you are seeing the formula for the series and parallel combination for the capacitance is the vice versa of the resistance. Series combination, parallel combination of resistance. For the resistances, series combination you are getting R net is equal to R1 plus R2 plus R3. But here for the parallel combination you are getting the C net is equal to C1 plus C2 plus C3. So here the resistance and the capacitor both have the reverse analogy. Right now, here the reverse analogy in the formula. So here you are getting the these two results for the series and parallel combination. I hope you understand the series and parallel combination. Let us discuss some numerical. So in this question, you can see here we have three capacitors such that this is the 2 microfarad capacitor and this one is the 1 microfarad capacitor and this one is also the 1 microfarad capacitor. And you can see clearly this 1 microfarad and this 1 microfarad capacitor is connected parallelly because both the head is 1 point, both the tail is 1 point, and the potential across both the capacitor is same. Potential difference across both the capacitor is same. That is why these two are in the parallel combination. And this 1 microfarad is connected with the series combination of this circuit arrangement. So you will write a simplified circuit. This is your A point. This is your 2 microfarad capacitor, and in place of these two resistors, we can use only one capacitor of rating. I am assuming it is C1. So this is your B point. So what is the value of this C1? So C1 is basically the C net of these two parallel capacitor. These two. So what is the formula for the C net in the parallel combination? You have the formula C1 plus C2. So here you have 1 plus 1 microfarad plus 1 microfarad is equals to 2 microfarad. Okay, so here the value of the C1 is 2 microfarad, and already this capacitor is given 2 microfarad. Now you can see that these two capacitors are connected in the series combination. So what is the total C net across AB? So the C net across AB, you will write the formula for the series combination. It is 1 upon C net is equal to 1 upon C net is equal to 1 upon C1 plus 1 upon C2. It is better to memorize the formula not in this form. You should memorize the formula like this one. C net is equal to C1 C2 upon C1 plus C2. Right? Both are same. If you take the LCM of the denominator, after that cross multiply, you will get the C net is equal to C1 C2 upon C1 plus C2. So here with the help of that formula, you just put the values. So C1 C2, so 2 into 2 divided by C1 plus C2, so 2 plus 2. After simplification, what you will get? 4 by 4, you are getting the 1 microfarad. So CAB, that means net capacitance across AB point is you are getting 1 microfarad. Right now? So I am revising again. These two capacitors are in the parallel combination. So I am assuming the C net of these two capacitors is C1. So what is the formula for the parallel combination? It is C net is equal to C1 plus C2. So 1 microfarad plus 1 microfarad. So that will give you the C1 is equal to 2 microfarad. Now you can see that this 2 microfarad or the C1 capacitor is connected with the series combination of this 2 microfarad capacitor. Now you have to apply the series combination formula, which is C net is equal to C1 C2 upon C1 plus C2. And put the values of C1 C2, you will get the 2 into 2 upon 2 plus 2 microfarad. So you are getting the net capacitance across AB point is 1 microfarad. Right now, so the various questions are given in your textbook. You should solve the series parallel combination of the capacitor. If you have any doubt, you should mention in the comment section. Thank you.